Impacts are an incredibly important topic in the field of engineering dynamics. The purpose of this video is to provide a background on the physical concepts behind impacts, how they relate to oblique impacts, present problem-solving methods, and to show a MATLAB simulation. An impact can be defined as a collision of two bodies that occurs in a relatively small interval of time and during which the bodies exert a relatively large amount of force on each other. In any collision, several definitions can be made. The line of impact is the common normal to the surfaces in contact with each other. If the mass centers of each object lie along the line of impact, the impact is said to be a central impact. Otherwise, it is called eccentric. If the velocities of each object lie along the line of impact, the impact is said to be direct. Otherwise, it is oblique. Now let's consider what actually happens during an impact. For now, we'll look at a direct central impact and relate it to oblique impacts later. Consider two particles A and B with mass A and B and velocities VA and VB. Because VA is larger than VB, A will eventually strike B. During the impact, they will undergo a period of deformation at the end of which they will have the same velocity u. Then a period of restitution takes place. The particles will either regain their shape or stay permanently deformed, and they will have final velocities VA prime and VB prime, which we are especially interested in. If we consider particle A and B as a single system, we see here that there are no external impulsive forces, so the following must be true by conservation of momentum. MAVA plus MBVB equals MAVA prime plus MBVB prime. We need another relation to obtain the velocities VA prime and VB prime given the masses and initial velocities, however. Let's examine the motion of particle A during the deformation. Before deformation, the particle is traveling with momentum MAVA until it is acted upon by an impulse due to a deformation force P from B expressed by the time integral of P. From the impulse momentum theorem, the initial momentum plus the impulse is equal to the final momentum MAU. Let's examine the motion of particle A during restitution. Before restitution, the particle is traveling with momentum MAU until it is acted upon by an impulse due to a restitution force R from B expressed by the time integral of R. From the impulse momentum theorem, the initial momentum plus the impulse is equal to the final momentum MAVA prime. The coefficient of restitution E is now defined. It is defined as the impulse due to the restitution force divided by the impulse due to the deformation force in an impact. It can range from 0 to 1. A value of 0 denotes a perfectly plastic impact, while a value of 1 denotes a perfectly elastic impact. Solving the two equations derived above for the impulses and substituting into the definition of E gives the following. A similar analysis of particle B would yield the following. Adding the two quotient values gives, which can be simplified into VB prime minus VA prime is equal to E times VA minus VB. This is our second equation and now allows us to solve for the final velocities of two particles if we know their initial velocities, the coefficient of restitution E, and their masses. Now let's examine an oblique impact. Recall when we defined an oblique impact as when the velocities of the objects are not directed along the line of impact. Consider this one. We have two objects A and B with masses MA and MB and velocities VA and VB not directed along the line of impact. We can draw another axis perpendicular to the line of impact. We'll call the line of impact axis N and the perpendicular axis T. We can split the initial velocities of each particle into components along these axes, so we have VAT, VAN, VBT, and VBN. We now consider conservation of momentum and impacts along each axis separate from each other. Notice that no impacts act along the t-axis. This means that the momentum of each particle is conserved along the axis. In other words, VAT is equal to VAT prime and VBT is equal to VBT prime. On the other hand, impulses do act along the n-axis, but momentum is always conserved and all impulses are internal to the system, so we can write the total conservation of momentum equation as we did earlier. This equation is MAVAN plus MBVBN is equal to MAVAN prime plus MBVBN prime. We can obtain one more equation by applying the concepts of the coefficient of restitution developed earlier in the video. Along the n-axis, applying the coefficient of restitution concept yields the equation VBN prime minus VAN prime is equal to E times VAN minus VBN. We now have four equations that can be solved for the components of the velocities of A and B after the impact. Once you know these components, you can assemble the final velocity vectors using trig. Note that the method of oblique impacts also works for problems in which a moving object collides with an immovable object, like a ball against a wall. In that case, you would still draw the scenario, find the TNN axes, but now you would only have 2 initial velocity components and 2 final velocity components. The components of the velocity of the second object would simply be 0. As you can see, oblique impact problems are mathematically rigorous and require a good understanding of vector mathematics to properly solve. An actual sample problem will not be completed in this video, but if the general method of solving problems is known, solving these problems should be relatively easy. Number 1. Locate and draw the t and n axes on the problem. Number 2. Resolve the initial velocities of both objects into components along the t and n axes. Using a transformation matrix may be of great use here. 3. Use the 4 conservation of momentum and coefficient of restitution equations to solve for the final velocity components. Note that this may require solving a 2-dimensional system, which is easily done with a calculator like a TI-89. And number 4, convert the final t and n components back into x, y, or ij form. Hopefully now you can see the theory and general method behind oblique impact problems. Alright, so now I'm going to test out the MATLAB program I wrote to do these problems for you. The program I wrote, you can give it an initial velocity and direction of the 2 objects in the oblique impact problem, as well as the line of impact angle and the coefficient of restitution, and it'll figure out the final velocities of each object. So we have a problem here. 2 identical hockey pucks are moving on a hockey rink at the same speed of 3 meters per second and in perpendicular directions when they strike each other as shown. Having a coefficient of 0.9, determine the magnitude and direction of the velocity of each puck after impact. So we'll go into MATLAB. We'll run our program. So we put in the mass of object A. Because it just says they're identical, it doesn't really matter what we put in. We'll just make sure both A and B are the same. So we'll say 1. The magnitude of the initial speed of A is given to be 3 meters per second. The angle of the initial speed of A with respect to the plus x axis is 0, because it's along the plus x axis. The mass of object B is 1 as well. Magnitude of the initial speed of B is also 3. And the angle of the initial speed, if you think about it being straight along the negative y axis, it would be 270 degrees from the plus x axis. The coefficient of restitution is given as 0.9, and the angle of impact is 20 degrees above the plus x axis. This will run some calculations, and it'll say the final velocity of A is 1.3 meters per second at an angle of 50.9 degrees below the minus n axis, and the final velocity of B is 3.85 at an angle of 47.2 below the plus n axis. So now you can find the plus n and plus t axes and figure out what these final velocities are in I and j based off of that. This will be in the description if you want to use it for anything.